Hello everyone and welcome back to my channel. In today's video, we are going to use the same R2Pay application which we have used in the previous video for bypassing some other advanced Frida detection mechanisms as well as integrity checks which are implemented in this app to protect it from being hooked. In our previous video, we have seen how to bypass Frida detections which are based on some Frida artifacts like process status files and some other file descriptor based artifacts. Now we are going to see some of these artifacts again today, but this time we will observe a different kind of implementation which makes it harder to identify such checks during the static analysis phase. If you remember from the previous video, we have bypassed these artifacts by hooking to this snprintf function, right? So I would recommend to go and check that video first. Link to that video is shown at the top right corner of your screens in the I button, as well as I'm going to drop the link in the description box. Now let's quickly try to spawn the application using Frida without attaching anything. So for that, in our terminal we can type frida-u and then tell it to spawn this package which is re.pawnme. Hit enter and we can see that the application is launched, but immediately it got crashed, and in the console we can see the crash log which says process crashed, bad access due to invalid address. And if you come down below here, you can see that it's a 6seg fault, which is a segmentation fault. And further going down in the backtrace section, we can see that the program counter is pointing at this address, which is the last address of the instruction that was executed, and it is present inside this libnative.so, right? So let me quickly split the terminal. And in the previous video, we have already decompiled this R2Pay APK using APK tool. So I'm going to that directory which is present at R2Pay. Then inside the library folder, we have architecture specific directory. So we are working with ARM64. And over here, you can see that we have this libnative.so, right? Now, in order to identify the cause and analyze what happened in this libnative library, we need to open it up using radare2 and see the disassembly of it. So for that, I'm going to use R2 and then pass the libnative library. Now before starting the analysis, make sure to change the analysis depth to 1000. For bigger binaries, I would recommend to always change this analysis depth to something big. Otherwise, radare will throw a lot of warnings. Now let's start the analysis using AAA command. Now based on the size of the library, it will take some time to analyze all the things inside it. Alright, so the analysis is done now. As you can see, currently it's pointing to FA30, but our crash occurred at this address. So let's copy this and seek to this offset using S command. So now we are at 3F980, right? And if we press capital V, we can go to the visual mode. And by pressing small p, we can see the disassembly of this address. Now we are into the disassembly view, and you can scroll up and down to see all the disassembled instructions. So our crash occurred at 3F980, which is here, and the instruction is LDR, which is load register instruction. So what it will do basically is whatever the value present in the address pointed out by this X10 register, that will be stored inside this W11 register, right? But in our crash log, we can see we got segmentation fault. So we can say clearly that whatever the address pointed out by this X10 register is invalid. So now we know that this is the instruction that is responsible for the crash, and it's present at this offset 3F980. So what we can do from here, if we try to analyze the instructions before this crash instruction, we can see that all the instructions, or most of these instructions, are just load and store instructions, and some of them are doing some kind of shifting and adding, right? Now to trigger any detection, some comparison has to be done based on which it decides whether to crash the app or not. So in ARM64, we have such conditional instructions available like cell, which is our conditional select instruction, and based on some condition, it will select the values of the register. Then we have set instruction, again based on some conditions, it will set the values of the register. Then other than these, we have some conditional branch instructions like branch equal to, branch not equal to. But as of now, in this particular basic block, we are not able to see any such conditional instructions present. But one thing we can see here is that this basic block is being called from this function, which is present at 1A690 from this offset, right? In such cases where our disassembler is able to figure out from where a particular block is being referred from, then it becomes easy for us to assume that this function could be the one which is responsible for some sort of detection. So from now on, let's call this function as our checker function, okay? But in some other cases, due to obfuscation techniques like indirect branching, disassemblers will not be able to figure out these cross references, which make it even harder to understand the flow. But luckily, this is not the case for us here. Okay, so assuming that this function is our checker function, let's seek to this address using s command, s, and seek to this address which is 1A690, right? Hit enter, and now we are into this function. And over here we can see that it is being called from two other places. One is from the data section and another one is from the code section. We can also manually check for the cross references using axt command. So if we do axt and then we want to check for this 690, 1A690, hit enter, it will show us the same results, right? One is this, another one is this, which is same as this one. All right, first of all, let's see what do we have here at this offset. So let's see to this address, and here we can see that this instruction, which is at 195cc, is actually pointing to our checker function. So the address of the checker function is stored into this x2 register, and then it is being passed as an argument to this pthread create function, right? Remember, in ARM64, as per the calling convention, the arguments to the function are stored in the register starting from. So the first argument is being stored into x1, second one in x2, third one is in x3, and then it calling the function that is pthread underscore create. Also, if you remember from the last video, in the end we have seen that the checks which we have bypassed earlier were triggered at regular interval in a separate thread, right? Which makes sense now, as we have this pthread create method which is calling our checker function as a separate thread. So it will continuously keep on checking our application for Frida artifacts or integrity checks. Although we are not sure yet whether this function is responsible for Frida artifact detection or for integrity checks. Now there can be multiple such checker functions present in the binary. So if we want to bypass all of them in one go, we need to somehow patch this pthread create method itself so that it will not trigger this function from anywhere. And in order to do so, we can directly patch it from the .plt section of the library. Now as you can see here, we are getting these shortcuts alongside with this branch instruction. So using this, we can directly go to the address where the implementation of this function is present, and since it's the function coming from an external dependency which is libc.so, so that's why the implementation will take us to .plt section. So if I press 1 here, we can see here now we are into the PLT section, and all the functions which are not part of this library and are coming from external dependencies can be seen here, like as isDigit, open, etc. So our pthread underscore create function is defined here at 5870. In order to patch or hook at any of these offsets which are present in this native library, we need to first identify the base address where this library is loaded in the memory at runtime. And for that, we first need to understand the concept of linkers. So in Android, linker 64 is the 64-bit version of the linker used for linking the shared libraries. It will resolve the dependencies between different object files and produces a single executable file. So this linker 64 is the first entry point which we can hook in order to figure out which shared library is being loaded into the memory by the application. Right, so let's go to our Visual Studio, and over here let's create a completely new script. Let's name it script v2.js. okay, and inside here we can identify or find the module by name using process.find module by name API, and here we can pass the name of our module, which is linker 64. Now in linker 64 we have do underscore dl open function, which is responsible for initializing the shared libraries at runtime. So whenever Android app is started or a new shared library is loaded, the do dl open function is called to locate the specified library from the APK. Then it loads it into the memory. All right, so we need to figure out the address of this do underscore dl open function present in this linker 64. So for that, we can enumerate over all the symbols of this linker 64, and this enumerate symbols will return a list of symbols present in this linker 64. So we can iterate over each of them using for each loop. Okay, and it will take a function. Let's give the argument name as symbol. That's it. So now it will iterate over each of the symbols. So we need to identify the symbol which has the name do underscore dl open, right? If it is greater than or equal to 0, then let's create a variable where we will store the address of this symbol. I will call it as do open. Initialize it with null initially, and now assign the address of this symbol to this variable through symbol.address. Okay. Now we have the address of this do_dl open function from linker 64. So using interceptor dot attach API of Frida, we can attach our hook to this do_dl open function. Then in the second argument we have this function, and inside this we can extract the library path which this function will try to load. So let's create a library underscore path variable, and we can get the full library path using x0 register. So context.x0, and the data type of this file path is character pointer, so we can read it using read c string method. So now we have the library path. It's normal in the applications that a lot of other libraries will also get loaded during the time of application launch. So to figure out when our library or our module is being loaded, we can apply this if condition. If library path is library native -lib.so, if it's greater than equal to 0, this means that our library is being loaded. All right, so for debugging, let me put a print statement here. Target library is loading. Now as you can see, I have put it as loading here because as of now the library is not fully loaded into the memory, it's in the process. So whenever the Android application gets launched or any new shared library needs to be loaded into the memory, this do_dl open function will be called, and it will try to locate the specified library from the APK file and loads it into the memory. It then calls the library constructors, which initializes the library data and the code segments. So during this time, and there is another method which will be called within this do_dl method, that is call_constructor, and it is used for calling the constructors of the shared libraries that are currently being loaded into the memory. So inside this call_constructor method, we can attach our hook and we can get the base address of the library, because by that time the library is loaded into the memory. So along with this do_dl open, we need another address, that is call_constructor. Let's assign it to null initially. Then here let's make another condition just like before. If symbol.name is call_constructor, then we will assign the address of this using symbol.address. Now inside this do_dl open, we can attach our interceptor to this call constructor like this. Then the second argument, we have this function, right? Now inside this we can get the base address, or we can actually get the complete module object. Let's store it in native mod variable. So again, by using process.find module by name and by passing the module which is libnative-lib.so, we can get this module. Now let's try to print it out in the console. Target library loaded at, and there we have our base address inside this native mod object. Alright, so now let's try to run the script and see what happens. So in our terminal, using Frida-u and passing the script, hit enter, and we can see that our target library is loading, and we got the base address of our target library as well. And as I already mentioned that inside this call_constructor, we are going to call our hooks in the future. So let's try to limit it out by making a simple logic using a flag variable. So if library loaded, let's assign it to 0 initially, and here we will check if the library is already loaded or not. So if it's 0, this means the library is not yet loaded. So let's extract the base address inside this. Otherwise our library is loaded, so we can assign it to 1. Right, now let's again try to run the script, and now we got this single time. All right, so this logic is important because otherwise it will create a lot of overhead at later point of time when we will attach our hooks. Okay, now coming back to our Radare terminal, where we have this pthread_create function which basically returns 0 if the thread creation is successful. Okay, so we need to patch this function in such a way that it will always return 0 irrespective of the passed arguments, and as per the ARM64 calling conventions, the return result will always be stored in x0 register. So what we are trying to do here is simply patch this instruction with move instruction and store 0 in our x0 register, and then in the next instruction we will simply return from here. So whenever our library calls this pthread underscore create function, it will assign 0 to x0 register and then simply return without doing anything or without actually creating a new thread. Alright, so in order to patch these instructions, let's go back to our script and create a new function here. Let's name it as patch pthread create. Okay, and we need our base address inside this, as we need to convert the offsets into the actual addresses in the memory during runtime. Now, in order to patch the instructions at runtime directly instead of modifying them statically in the SO binary, Frida provides us this memory.patch code API. Okay, and it takes 3 arguments. First one is the address of the instruction which we need to patch. So for us, that is 5870, right? So let's convert this to actual address by adding it to the base address 5870. Then the second argument is the length of the instruction. Now in 64-bit architecture, the instruction length is 4 bytes, and there is the dynamic way also, so let's use that. So using process.page size, we can get the length of the instructions. Then the third argument is the code, which is a function inside which we will define our function which we are going to replace. Okay, so for that, let's create a variable with the name cw, then initialize it with ARM64 writer. This ARM64 writer basically contains a lot of utility functions like put NOP, put return, and many more. So these utility functions will directly put the instruction at the specified memory address so that we don't have to manually convert the instructions into byte form. Right, so this function takes 2 arguments. First one is the code itself, which we have defined here, right? Then the second one is the JSON like object, which has program counter as the key. So we need to set the value of program counter to the instruction which we are going to modify, which is this one, right? So I'm going to copy paste it. All right, now using this cw variable, we can access all the functions available in this ARM64 writer. For now, we are going to put instruction function of this class, and here we are going to write hex equivalent of move instruction. So what we are supposed to do here, we are going to replace this first instruction with move x0 comma hash 0, right? Because we are need to put 0 into the x0 register. So for the reference, I'm going to write it here. That's what we are going to put. But this put instruction takes the input in hex form, so let's convert it in the hex equivalent form. So for that, we have online utility available, which is armconverter.com. And here in the assembly code, you can put any ARM64 instruction and it will convert it to hex equivalent. So for example, we need a hex equivalent of that move instruction, right? So let's put it here, move x0 comma hash 0. The hex equivalent of this is this one. So for reference, I am going to paste it here. Now before passing this as an argument to this put instruction function, make sure to put it in a reverse order because our system uses little Indian formatting. So for that reason, we need to put it in reverse order. So we can put it like this, D2 800000, right? And then for debugging purpose, let's put a console and print out the instruction which we have patched. So we have patched the instruction, and using instruction.parse API, I am going to print out the instruction present at this address. So after patching, this will print out the updated instruction that should be move x0, right? Now similarly, we need to patch the second instruction as well, which is present at this offset 5874. So I am simply going to replace this with 5874. 5874, 5874. All right, and instead of move instruction, now I am simply going to return from this function. So I need to put the return instruction, and let's see what the hex equivalent of this return instruction is. So the hex equivalent is this one. Again, need to put it in the reverse order. So D6 5F03 C0. That's it. Now we can call this method inside our call constructor, and here we can pass the base argument using this native mod object and access the base address through base. Let's save the script now and go back to the terminal, clear it out, and launch the script again and see what happens. Yes. So as you can see in the console, we have our updated instructions here, and the application is up and running now, as you can see in the device, and it's not crashing anymore, at least at this screen. So we have bypassed our first check, right? So let's now try to generate our R2 coin by entering some random pin, let's say 2580, and the amount, let's say 500, generate coin, and the application crashed. And in the console we can see the crash log, and the crash is happened again due to bad access, due to invalid address, right? So it's a segmentation fault again, but this time the crash occurred at this offset dbc3c inside this libnative library. Right now let's try to do the same thing again. We have the crash at this offset, right? So let's seek to this offset in our radar 2 terminal using this s command, and now we are at our crash address. And again, if you see, the crash occurred due to the ldr instruction, which looks similar to the previous one. So whatever the address pointed out by this extend register, that is invalid. And if we scroll up, we can see again a similar pattern, and this is the basic block of this crash instruction, right? And this time we can see that we don't have any cross references to this basic block. And let's try to confirm this manually as well by using axt command. So we need to check for the cross references to this offset, and it's not returning anything. So our disassembler is not able to resolve the cross references to this basic block. So during the static analysis, just by looking at this disassembled code, as of now it's not possible to identify from where this basic block is being triggered. So what might cause this crash to trigger? So since we are not able to figure out from where this crash routine is getting called, so we need to think logically what might cause this crash to trigger. Since we are not using any kind of debugger, so debugger detection is not applicable here. Then we are left with two possibilities. Either this could be because of some other Frida detections, because obviously our Frida server is running and we are trying to hook onto the instructions, or because of integrity checks. And these integrity checks will get triggered whenever we hook onto any address, right? And that's what we are doing. Now from here, as the next step, what we can try to do is to hook some of the interesting imported functions, just like what we did in our last video. So in our radar, by typing ii command, we can see all the imports, and the interesting ones which we have figured out earlier also are open function, smprintf function, lstat function, str function, which is used to compare the strings, right? So let's see whether this crash is occurred due to any of Frida artifacts which are being called via these imports. So let's go back to our script and create a function with the name hook imported functions. All right, now in this case we don't need to pass our base address because these imported functions are coming from external dependencies. Now we can quickly copy our some of the imported functions which we have hooked previously, which is smprintf, lstat, and open. So just copy paste these. So here we have hooked on to the smprintf, then here we have hooked on to lstat, then here we have hooked on to the open function. Okay, for now let's remove these conditions because we just want to see what's being called and what file paths these functions are trying to access. All right, other than these functions we have str also. So let's try to hook this str function as well, just to be sure that we are not missing out onto anything. And this str function takes two arguments. First one is the string argument, and the second argument is also the string to which the first argument will be compared to. So for that reason I'm just going to print both of these arguments. args1.read string. Okay, now these hooks are independent of our libnative module, so that's why we can call this function anywhere, right? So let's call it at the top. Now run the application again through our script and see what happens. Okay, so we can see that we got a lot of output in the console. So these all are from the str, and as of now nothing seems specific to Frida artifacts. Then we have open functions, then smprintf, then again str, but nothing specific to Frida artifacts. Then we do have some open functions which are pointing to the su binaries, which is used for root detection logic. But since we are using the GIGISC module inside of Magix Manager to bypass root detections, so there is no need to manipulate these arguments to bypass root detection, as it's already been taken care by the GIGISC module. So we were getting crash at the time of coin generation. So if we try to generate the coin again, we can see that again root detection checks are being called, but nothing other than this. Now we can be sure that at the time of coin generation, these imported functions are not contributing to any of the checks other than the root detection. Now again, if we see the crash log, we got this segmentation fault at this address. So if you observe it closely, so you need to be very careful in observing these crash addresses, because every time it will get changed whenever something happens, right? So now if you noticed previously, before hooking our imported functions, the offset was different, but after hooking our imported function, we got a new offset address, that is D36F4. So again, what we can do is we can seek to this crash offset D36F4 in our radar array, and we can see now again we have this LDR instruction, and if we scroll up we can observe the similar pattern, right, as before. So this basic block again is the block which is responsible for the crash, and again this time also radar 2 is not able to resolve the cross references for this block, right? So now what else we can do here? Let's try to figure out the subroutine where this basic blocks belongs to, and in order to do so, we have this pdr command. So what it will do basically is it will try to print the disassembly of all the basic blocks recursively from the subroutine to which they belong. And if we hit enter, and since it's a huge function, it's asking us to show all the lines which are more than 90,000. And if we hit Y, it will print out the complete block of subroutine to which this belongs to. So if we go all the way up, yep, here we ran our pdr command, and the function to which this offset belongs to is this one. All right, so just make a note of this function. And as you can see here, if we try to apply the same logic which we have applied to identify our checker function at the time when we bypassed it by patching the pthread create function, we were able to see the cross references from where this function is being called, right? But here our disassembler is not able to resolve it. There can be multiple reasons for that: good obfuscation, indirect branching, and stuff like that. So statically it's not possible for us to figure out at this point of time from where this function is getting called, and hence we cannot bypass this just by patching some instructions. But one thing we can be sure of is that this is the function which is responsible for our checks, right? Because the previous crash address before this was also in the range of this subroutine. Okay, so let's think what else we can try. So if we think about some of the other ways in which an ARM64 library can call a function without being visible in a disassembly, and one way to call a function is by making use of supervisor call, that is SVC instruction, right? But before proceeding with this approach, first let's be sure that these instructions are present in this native library or not. So back to our radar terminal, we can search for any specific instruction by typing the command /ad and then the mnemonic which we are looking for, that is SVC. Hit enter, and we can see that there are a lot of SVC instructions present in this binary, right? Which is good for us because now at least we have something to start with. Now before beginning, let's try to understand how these SVC instructions work. So SVC stands for a supervisor call instruction, which is used to generate a system call from an application. Okay, when the SVC instruction is executed, the processor switches from user mode to privileged mode and jumps to a predefined handler in the operating system, which then services the system call. And once the service is complete, control returns back to the application that made this request. Now the question is how this supervisor call knows which function to call. So this will be decided by the system call number, which needs to be set before calling these SVC instructions. So to better understand this thing, let's have a look at the SVC table, which I have already opened for you. So this table is for ARM64, and here we can see the system call name along with its arguments, right? So for example, let's say we are looking for open function. So in the system call name, let's look for the open function which is present, and it's present here, right? So this is the openat function which has the system call number 0x32, right? And its equivalent integer number is 56. Okay, and then we know that this openat function takes 2 or 3 arguments. So all these arguments are stored by a specific register. So for example, the first argument, which is the file descriptor, will be stored in this x0 register. Okay, similarly, the second argument for this, that is the file name, will be stored by this x1 register, and so on. Okay, so if we go to our disassembly, and let's say we want to check the arguments being passed to this svc instruction, so let's seek to this offset. Okay, hit enter. So here we are at this offset where our svc instruction is present, and if we scroll up, we can see the arguments which are being stored in the respective registers. So in the x8 register, system call number will be stored, then in the x0 register, first argument will be stored, and so on. But if you notice here, by looking at this assembly, we cannot say which system call it's actually trying to execute here, because all of these arguments values are coming from the stack at runtime. So this is something that is been implemented in this library very smartly, so that we will not be able to figure out the system call that are being executed, at least statically. Now we are left with only one option, that is to hook all these svc instructions and print out the arguments. Now let's go back to our script and create a function. Let's name it as hook svc instructions, and we need our base address here, so let's take it as an argument. Now we need an array of all these svc instructions which are getting called inside this native library. So for that, actually Radare provide us a very good command which will return all the svc instructions along with their offsets in a JSON format, which we can then directly use in our script. So for that, in our terminal, we can do a quick search as we did before, /ad, and then append j, which will convert the output into JSON format, and then the mnemonic, that is svc. Hit enter. And as you can see, now we got the output in a JSON format with the offset and the instruction, right? So let's copy it and paste it here. Constant address is equals to like this. Now we can iterate over all these offsets one by one and attach our interceptor, right? So this way we have eliminated the need to manually attach the interceptor one by one on all these addresses. So this is a very useful command to get the output in JSON format. Now let's iterate using for each loop on this address variable. We can apply for each loop directly, and this takes function as the argument. Let's give it as svc. Now inside this for each loop, we can apply our interceptor, but we need to convert these offsets from this JSON to hexa equivalent. Currently they are in the integer format, right? So for that, let's create a variable with the name offset, and we can access this offset key using this svc object here through the dot operator. So svc dot offset, and then using toString method, we can convert it into a string format, and if we pass 16 as the argument, we will get the hexadecimal equivalent of this number, right? But note that this will not return us the hexadecimal value in an address format. So for that, we need to append 0x in front of it and append it through string concatenation like this. And now we have the complete address of these offsets, and now we have these offsets in hexadecimal equivalent form. Right now we can attach our interceptor like this to these offsets, but we need to add it to our base address to get the actual address. All right, then the second argument would be our on enter function. It takes one argument, and inside this, for now, let's just try to print which svc instruction is getting called here. So for that, we can print out the offset directly, and let's see which instruction, and let's see which system call number is getting executed. So for that, I am putting svc hash, and then we can extract the system call number by accessing the x8 register. So if you remember here, in this system call table, we can see that system call numbers are stored in x8 register, right? And these are in hex format. So using our context, we can access this x8, and let's convert it into the integer representation using 2 and 32. All right, let's save the script, call this function inside our call constructor, okay, and pass the base address like this. And let's go back to the terminal, clear it out, bring our screen on the top and launch the script again. Now as we can see, a lot of SVC instructions are getting called, and they all are 63, right? And in the UI our app is currently stuck. So if we go back to the system call table, we can see that 63 is actually our read function, right? And something went wrong, I guess. And yeah, in the console the process got terminated. So nothing to worry about. This actually happened because our script is generating a lot of output in the console, which is creating a lot of overhead for the application, due to which it might run out of memory and it got terminated, right? So to avoid that, we have already noticed that it's trying to read file or something continuously from this offset. Okay, so just keep this in mind. And also it is possible that we are not able to see other SVC instructions because of this constant output. So let's try to filter it out in our script. Over here we can simply put a condition. What basically we are going to do is we are going to print all the SVC instructions which are not equal to 63. This way we will get a chance to see some other SVC instructions if they are getting called or not. So let's clear the script again and launch it. All right, so the application is launched, and in the console, if you have noticed earlier, you can see that it called some other system calls like 56, 57, then again 56, then 62. So let's see what these system call numbers stand for. So 56, by going back again to the documentation, 56 is our openat function. All right, then we have 57, which is close. So by the sequence of these SVC instructions, we can assume that the application is trying to access a particular file using this openat function, and then after reading it is closing it, right? Then we have 62, which is lseek. Okay, so let's do one thing, exit this and go back, and here try to print out the arguments for the openat function call. So for that we need to put the condition again. If the system call number is equal to 56, which is openat, right, then let's print the offset and the SVC number as it is, along with the argument or the file path. So in the openat function, if you see here, it takes this file name as the second argument, which is stored inside this x1 register, right? So for that reason we can access it using context.x1, and since it's a character pointer, we can read it using readCString method. Save the script, go back to the terminal, clear it out, launch it again. All right, go back to the top where our SVC instructions are executed, and here now we can see that SVC 56 is triggered and the file name was procself map. Similarly, next time it's trying to access this libc.so, then again maps, and then again libc.so, right? But the application is running properly without any problem, so these calls are not causing any issue as of now, so we can ignore these. Let's go down, and now let's try to generate the R2 coin again and see at the time of generation if any of other SVC instructions are called or not. Generate coin, and now we can see that the application is crashed again due to bad access, and the reason was segmentation fault, and it crashed at this address. And if we see our SVC output in the console, it's trying to access proc self status file, right? And then we have our open functions which are trying to access su binary, which we have already bypassed using JGISC module. So nothing other than this which is related to Frida artifacts as of now. And this file, so I'm just trying to give you a little bonus tip here. This proc self status file is used to check whether the process is running under a debugger or not. So when you try to debug the application, this particular file is responsible for the detection, and you can bypass it by passing the fake status file to bypass debugger detection. Okay, but since we are not running the application through any kind of debugger, so this condition is not applicable, and this is not the reason for this crash. So still there is no sign of Frida artifact being accessed, right? So at this point of time we can assume that this crash is happening because of some sort of integrity checks. So to understand the control flow and the logic what causes this crash to happen, let's seek again to the crash offset, which is B90A4, right? So in our Radare terminal, we can go to this offset like this, hit enter, and if you can see here again we got this load register instruction, and if we scroll up, it is same sort of pattern, right? This is the basic block. So ideally for integrity checks, how it works is basically there will be some hard-coded hashes of .text section of the library, and then a separate thread or sometimes inline code will compare these hard-coded hashes with the hash generated at the runtime during the comparison, and if it matches, then integrity check is passed, otherwise it will be considered as failed. And since we have already patched our pthread create function, so we are sure that these checks are inlined and spread throughout the code, which makes it difficult to bypass in one go. So we have to now trace down each instruction one by one and try to find some sort of pattern or relations based on the output. And here if we try to figure out something, again we can see that other than load and store instructions, there is nothing much in this particular basic block. As I just mentioned, for integrity checks it has to make some sort of comparison, right? And for comparison we have some conditional instructions in ARM like CCell instruction, which is conditional select. So based on some condition it will select a particular register value. Then we have conditional branches like branch equal to, branch not equal to, which are again missing here, right? So the only way left out is to trace each instruction one by one. So we have to trace down each instruction one by one, and we will try to find some pattern or relations based on the output. And for tracing the instructions, we are going to use Frida stalker now. If you don't know how to use Frida stalker, then I have already made a separate video about Frida stalker, which you can go and watch, and I am putting the link of that video in the description box, as well as it will appear on your top right screen in the I button. So let's start creating a new function in our script. Let's name it as stalker, and here again we need the base address, right? Then let's write the basic boilerplate code for the stalker, which is stalker dot follow, and it takes two arguments. First one is the thread ID which we want to trace. So here we want to trace the current thread ID of the process. So for that we can use process dot get current thread ID, and it will give us the thread ID of the running process. Then in the body we have transform function, and in the argument it gives us an iterator. So using this iterator we can iterate over each of the instructions one by one and print them out, right? All right, now in our transformer body we can get the instruction through this iterator, and we are going to store it in this instruction variable. Okay, now in order to iterate each instruction one by one we need to loop over it, and for that we are going to use do while loop. Then inside this do, let's simply try to print out the instruction which is currently being executed. Along with the instruction, let's also print the offset of the instruction so that we can trace it in our disassembly. So for that we have this instruction variable, and through this object we can get the address like this, and by subtracting it from base address we can get the offset, and along with this offset we can print the instruction itself. Okay, this needs to be inside this single quote. Then we need to call iterator.keep method, and here in the while we need to put the condition till when this loop will execute. So we want it to continue execute until all the instructions gets executed. So for that let's use this instruction variable, and using the iterator.next iterate over it until we receive null instruction. All right, now one thing, it's not recommended to call this stalker method directly inside your call constructor, because it will create a lot of overhead for the linker during the initialization phase, which can cause the app to crash at runtime. Okay, so instead of that it's better to always call this stalker within a certain range. So for that the best place would be the function where our crash offset is present. So we can get the actual subroutine where this crash instruction is present using pdf command. So it will try to disassemble all the basic blocks which are present inside the subroutine where this offset resides. Since it's a very big function which is almost 80,000 lines, that's why it's asking us to print them or not. Let's hit yes, and it printed all the instructions which are present in that subroutine, right? So just for the future references, let's note down the end address of the routine, which is EED8, right? Then let's figure out the starting address for this subroutine. Okay, so the function name is this, and it's starting from 9B438. Let's copy the starting offset of this function to our script like this. So now the function which is responsible for the crash is within this range, right? So it would be better to attach interceptor directly to the beginning of this function, because most likely if this is the function responsible for the crash, then it will be triggered, and inside that hook we can call our stalker function directly. So let's make a function and name it as hook tracer. Now let's save the script and go back to our terminal, clear it out, bring our device on top of the screen and execute the script again. we can see that our application launched normally. And now when we try to generate the coin, we should be able to see our instructions through the stalker. So let's put the pin and the amount, generate coin, and there you go. In the console we can see that it's printing a lot of instructions. Some of the instructions which have been printed by this stalker are not in the range of the library, as you have noticed over here. So to limit that out and to avoid unnecessary instructions in the output, let's put one condition here. If instruction dot address is greater than equal to base address dot add this offset, and instruction dot address is less than base address dot add the ending offset of the function. And if that is the case, then only we will print the instruction in the console. So what we are trying to do here is we are simply limiting our output, and it will now only print the instruction which are within this range, right? Save the script, go back to the console, clear it out, and run the script again. So we have the application launched. Let's try to generate the R2 coin. Alright, so in the console now we can see that the stalker output is being generated and the application got crashed. So the last instruction executed before the crash is present at this offset, which is a branch instruction, right? And in the crash log, we can see that the crash occurred somewhere at this offset inside anonymous, which is not our libnative library, right? So we can ignore this crash and let's just focus on the tracer output for now. So if you remember, I have told you already that for the integrity checks, conditional statements or conditional instructions have to be responsible, because based on some conditions, the application decides whether to crash the application or to execute it normally, right? And if we go above in the tracer output, we can see that we have this conditional select instruction present, which is getting called. And if the zero flag is not equal to 0, then it will consider the value of W14 register, otherwise it will consider the value of W15 register, right? And based on that we will get the output. Now just by looking at this traced output, it's not very clear from where the zero flag is being set, because there are a lot of operations being performed here. So instead of identifying the exact logic or the exact flow, what we can try to do is to simply patch out this conditional select instruction, and normally you will find the culprit instruction closer to the last instruction which is executed. Okay, so this is the only conditional instructions we have so far. So if we patch it with the NOP instruction, it will start executing from the next instruction. So let's try to do that and see what happens. Going back to our script, here we can create a new function. Let's name it as patch offset 1, and here we need our base address, so let's take it as an argument. Then in the body, as we have already seen, Frida provides us this memory dot patch code API to patch the instructions at runtime. And here the first argument it takes is the actual address where we need to patch the instruction. So we need to patch this instruction which is present at this offset, so let's copy it, and here we need to add it to the base address like this. Then the second argument is the length of the instruction, which in 64-bit is 4 bytes, right? But we can get it dynamically using process.page size also, so let's use that. Then in the third argument, we need to provide this code body where we will write our replacement instruction. Inside this body we can decide which instruction to patch. So for that, let's create a constant variable and assign it to ARM64 writer. Okay, now this ARM64 writer takes two arguments. First one is the code itself, which we have defined here, and then in the second argument it will take a JSON like object where we will assign the program counter register to the instruction address which we are going to patch, right? Like this. Now using this CW variable we can patch the instruction with the one we want. So in this case we want to patch it with NOP. So this ARM64 writer class provides us with lot of functions for the instructions directly, so that we don't need to convert each of the instructions into the byte form in order to write it into the memory. So for patching NOP instruction we have put an OP method, and this will replace the instruction at this address with NOP, right? Then in the console, just for debugging purpose, we are going to print out the patched instruction like this using instruction.parse, and our updated instruction is present at this address. Okay, Now let's call this patch offset one function in our call constructor here and pass the base address using native mod.base. Okay, let's save the script, go back to the terminal, clear it out, launch it again, and let's try to generate the coin again. And in the output again we are getting a lot of traces, but again it got crashed, right? And this time the last instruction executed is B91C8. And if we go up again, we can see similar kind of instructions which we have seen previously. Now due to these many instructions, it's getting a little bit difficult to identify the C cell instruction, whether there is any C cell instruction or not, which I can see here. We have one. So just to make it more visible, what we can do in our stalker function, let's only print out the instructions which are conditional select instructions. So for that we can make use of the instruction dot mnemonic, and if it is C cell instruction, then only we are going to print out our instruction, otherwise we are not going to print it out. So this way we will get more clear idea about how many conditional instructions are being triggered and what is the last one. So let's run the script again, try to generate the R2 coin as usual, hit enter, and there we go. We have these many conditional select instructions being executed, but the last one executed is this one, which is at B9044, right? So let's now try to patch this one. I'm copying it, and in our patch offset function, instead of creating a new one, we can simply replace it, because there will be only one conditional select instruction which is causing this crash to occur. So we can try patching them one by one. Save the script, clear the terminal, launch the script again, and again generate the R2 coin. And this time we can see that the last conditional select instruction executed is this one, which is present at B8EC4. So let's copy this, and in our script, instead of this one, let's patch this instruction. All right, save it again in our terminal, launching the application, generating the coin. All right, now what we can do, let's try to reduce some overhead from this script. So in the call constructor, we don't need hook tracer anymore. Then so far we have not seen any use of this str function and this lstat function. So let's remove these. Now going back to our console, and let's see what do we get in the output. And now if we try to generate the coin, we can see in the output this time our crash occurred at this address inside our libnative.so, right? And in the console itself you can see that now we are getting some other Frida artifact file which are being accessed using snprintf function, and these are the same files which we have patched in the previous video, right? And these files are also being accessed through this svc78. So what the svc78 is, it's read link at, right? So after accessing this file, it's trying to read it using read link at function, which is being triggered using svc78 system call. So we have already seen how to bypass these Frida artifacts, and for that what we are going to do is, from our previous script in our hook snprintf, we have applied these conditions, right? So in our console as of now, all these are from the file descriptors. So let's copy this condition and put it here in our snprintf function above our console statement, so that we can see the final output after modifying it. So going back to the script and launching it again, generating the R2 coin, and this time in the console we can see that all these file descriptors are now only accessing this 45 number, right, which we have provided here. So this check has been bypassed now, and after these file descriptors check, the application is trying to check for this status file. So we need to patch these also. And if you remember this 56 svc instruction, this is what, openat, if I remember correctly. 56 is openat, right? So it's trying to access the same status file using these svc instructions also, and through snprintf also. So let's put this condition where if the application try to access the status file, we are going to replace it with a fake status file. And how we have generated this fake status file, this I have already explained you in the previous video. Let's save it. Going back to the console, clear it, launch the script again. And let's see what happens this time when we try to generate the coin. Bingo, our coin is generated now. And all our snprintf functions have been replaced by fake status. And also, if you notice here, these svc instructions have also been modified automatically with this fake status file, which we have not did in our script intentionally. So from this we can see that there is a bug in this logic, where whatever the argument passed to this snprintf function, that same argument is being accessed in this supervisor call, right? So now we have modified and patched all the checks which are present in this R2Pay application, and now we can generate the coins easily. So that's all in this video. Also, before going, one thing I would like to mention is that this patch offset, this might be different for some of you depending on the way you are trying to attach the hooks and on the functions you are attaching the hook. All right, thank you, and I hope to see you in the next video very soon. And also don't forget to subscribe to the channel, as it is very important for us and motivates us to keep making such videos.